2 minutes ago, a telescope camera the size of a small elephant finished processing a single frame of sky over the Chilean desert. Nobody in that control room expected what came out of it. Researchers had planned for a calm first look, a quiet calibration image meant to check that the instrument worked the way it should. Instead, they got something that made several scientists stop what they were doing and lean closer to their screens. Buried inside that one frame was a detail nobody had put on the checklist, something that should not have been visible yet, something that made a few people in that room quietly ask each other if the software had made a mistake. It had not. This is the story of the very first image ever released by the Vera Rubin Observatory, and why astronomers are still talking about what that single picture accidentally proved. Before you hear what it actually showed, you need to understand why this telescope was built differently from every other eye we have ever pointed at the sky, and why that difference is the entire reason this first image turned into a scientific shock instead of a routine photograph. To understand why one picture caused this much attention, you have to understand what this instrument was actually designed to do. Most telescopes are built to stare. You point them at one object, you gather light for hours or even days, and you get one incredibly detailed picture of one thing. The Vera Rubin Observatory was not built for that job. It was built to scan the entire visible sky over and over again every few nights for 10 straight years. Scientists call this project the Legacy Survey of Space and Time. The idea is simple to explain but hard to build. Take a picture of the whole southern sky. Wait a few nights. Take the same picture again. Then, let a computer compare the two and flag anything that changed. A star that moved, a light that brightened, a dot that disappeared. According to teams at SLAC National Accelerator Laboratory, once this system runs at full strength, it is expected to generate around 7 million of these change alerts in a single night. That number is difficult to picture, so try this instead. Every previous survey of the sky produced a handful of alerts a night that a human team could actually look through by hand. This one produces more alerts in a single night than most observatories used to produce in a year. But before any of that 10-year survey officially started, engineers needed a first test image, a kind of proof that the camera worked. That test image was supposed to be boring. It was supposed to show that the mirrors lined up, that the sensor recorded light correctly, and that the software could stitch thousands of smaller exposures into one giant picture. Researchers were not hunting for a discovery, they were checking a machine. And that is exactly why what happened next surprised so many people. Nobody was looking for anything unusual, because on paper this was not the kind of image where you expect to find anything unusual at all. It was a systems check. And systems checks are not supposed to make astrophysicists cancel their weekend plans. When the imaging team finally stitched the first full frame together, they were looking at a patch of sky centered on a well-studied region near the Virgo cluster of galaxies. This is an area astronomers have photographed for decades. Older telescopes had already mapped it in fine detail. So the expectation was low. Everyone assumed the picture would confirm what earlier instruments had already shown, just with a slightly sharper camera. Instead, researchers noticed a faint arc of light stretching across a section of the frame that no earlier survey had ever flagged. It looked, at first glance, like a scratch on the lens or a processing error, the kind of artifact engineers usually delete before anyone even sees the final picture. But when the calibration team checked it against the raw sensor data, the arc was real. It was light. It was coming from somewhere in deep space, and it stretched across a distance so large that early estimates placed it at well over 100,000 light-years from end to end, a scale that dwarfs the width of our entire galaxy. Scientists now suggest this faint structure is likely the stretched-out remains of a smaller galaxy, torn apart slowly over millions of years by the gravity of a much larger neighboring galaxy. In simple terms, one galaxy may have been eating another one for a very long time, and the evidence of that meal was smeared across the sky in a thin trail of stars so faint that no previous telescope had the sensitivity to notice it. This matters more than it might sound like at first. Every earlier survey of this exact region had access to the same stars. The stars did not move. The galaxy did not appear overnight. The stream had almost certainly been sitting there the entire time. What changed was not the universe. What changed was the camera's ability to see something that faint. Older instruments were essentially squinting at a whisper. This new instrument was built to hear it clearly. Astronomers have started describing this shift in a specific way. They say older surveys captured moments, while this observatory is designed to capture patterns across time, almost like giving the sky a form of memory. And a sky with memory does not just show you what exists, it starts showing you what has been quietly happening the entire time nobody was paying close enough attention. So if a routine calibration image, taken purely to test the hardware, already contained a hidden galactic scar this large, the obvious next question becomes impossible to ignore. What else did that same test image accidentally capture? As it turns out, the stretched galaxy was not even the most talked about detail hiding inside that frame. Something small, fast, and almost impossible to explain was moving through the same picture, and almost nobody noticed it until a data analyst ran one extra check 3 days later. 3 days after the first image was released to the public, a graduate researcher working on a separate project decided to run a routine motion detection script across the same calibration frame, mostly out of curiosity. The script is designed to catch anything that shifts position between two exposures taken minutes apart, the kind of tool normally used to spot asteroids. Nobody expected the test image to contain one, since it covered such a small patch of sky for such a short amount of time. But the script flagged something anyway, a single point of light that had moved just enough between exposures to register as real motion rather than noise. When the team checked the object more closely, they realized it was a small asteroid, one that had never been recorded in any existing catalog. On its own, that would not be shocking. New asteroids get found constantly. What made this one different was its brightness pattern. As the object crossed the frame, its light flickered in a rapid, repeating rhythm, brightening and dimming in a cycle that repeated roughly every 2 minutes. That kind of fast flicker usually means one thing: the object is spinning, and spinning fast. Researchers estimated its size at somewhere between 400 and 700 meters across, roughly the length of several football fields placed end to end. An object that size, spinning that quickly, immediately raised a red flag among planetary scientists who study these bodies for a living. Most asteroids in this size range are what scientists call rubble piles. They are not solid rock all the way through. They are loose collections of boulders, gravel, and dust, held together by nothing stronger than their own weak gravity, similar to a pile of loose stones barely resting against each other in space. A rubble pile spinning as fast as this one appeared to be spinning should, according to standard physics, start flying apart. Centrifugal force should overpower the weak gravity holding it together, scattering debris outward instead of keeping the object whole. Yet this object showed no sign of breaking up. It stayed intact, its brightness cycle steady and repeatable across multiple exposures. One planetary scientist reviewing the data described the rotation speed as sitting well outside the range anyone expected for an object of this size, saying that most rocks this large simply are not supposed to spin this fast without falling apart. So what is holding it together? Researchers have proposed a theory that sounds almost like science fiction, but is grounded in real physics. Some scientists suggest that unusually fast-spinning asteroids like this one may not be ordinary rubble at all. Instead, they may be dense fragments broken off from the metallic or rocky core of a much larger body, a planet-sized object that existed early in our solar system's history and was later destroyed in a violent ancient collision. If that theory holds true for this object, it means the tiny point of light captured almost by accident in a routine test photo could be a surviving piece of a planet that no longer exists, spinning quietly through space for roughly 4 billion years before a graduate student's curiosity finally noticed it. And here is the detail that turned this from an interesting footnote into a bigger story. Once the team went back and checked slightly wider portions of that same first image dataset, they found evidence for at least a dozen additional fast-spinning objects hiding in the noise, several of them rotating in under 10 minutes. That is a discovery rate that, under older survey methods, might have taken years to match. This single calibration image, meant only to test hardware, had apparently stumbled onto a small cluster of objects that challenge current assumptions about how asteroids form and hold together. Researchers now believe that once the full 10-year survey begins operating at complete strength, similar fast rotators could be found by the thousands, each one a potential fragment of solar system history that has never been read before. But asteroids were not the strangest thing that first image accidentally captured. Buried in a quieter corner of the same frame, almost invisible unless you knew exactly where to look, something else had changed between exposures, something that had nothing to do with rocks or motion at all. While engineers were still celebrating the asteroid find, a separate team working on transient detection, meaning objects that brighten or fade suddenly, noticed something odd while comparing the new calibration frame against archival images of the same patch of sky taken years earlier by a different observatory. In one of the older images, a faint star sat quietly in a crowded field, unremarkable in every way. In the brand new Rubin frame, that star was simply gone, not fainter, not shifted, gone, as if it had never existed at all in that exact spot. At first, the team assumed this was a processing glitch, since missing stars are usually explained by a bad pixel or a masking error in the software. But after manually checking the raw sensor readings twice, the star's disappearance held up. Researchers now suspect this may be evidence of what scientists call a failed supernova, one of the rarest and strangest kinds of stellar death currently known to physics. Under normal conditions, when a massive star runs out of fuel, it explodes outward in a supernova, a blast so bright it can briefly outshine its entire home galaxy. That kind of explosion is loud, visible, and almost impossible to miss from Earth. A failed supernova works differently. Instead of exploding, the star's core is thought to collapse so completely and so quickly that it folds directly inward into a black hole, without producing the bright flash normally associated with stellar death. There is no explosion to see, there is only an object that used to be there, and then quietly is not. For decades, this kind of event existed only in theoretical models, because catching one in real data is extraordinarily difficult. You are not looking for something bright appearing in the sky. You are looking for something ordinary quietly vanishing from it, buried among millions of other stars that all look similar until one of them stops existing without any warning at all. One astronomer involved in reviewing early Rubin data explained that this observatory is uniquely suited to catching exactly this kind of event, since its images can detect objects far fainter than most previous ground-based surveys were ever capable of recording. In plain terms, older instruments were simply not sensitive enough to notice this specific kind of silence. If this particular vanishing star is confirmed through further observation, researchers say it would count as strong supporting evidence that some massive stars die without any explosion at all, collapsing directly and silently into black holes far more often than scientists have previously assumed. That would mean there may be significantly more black holes scattered throughout the universe than current counts suggest, simply because most surveys were never built to notice a star going quiet instead of going bright. This single detail, found almost by accident inside a test image meant only to check camera hardware, connects directly to one of the biggest unanswered questions in modern astrophysics. How often do massive stars actually explode? And how often do they simply disappear? Researchers now suggest that once the full 10-year survey reaches its planned operating pace, this same detection method could be applied across the entire visible sky every few nights, potentially uncovering dozens of similar silent collapses that would have been completely missed under older observing methods. And there is a second reason this particular test image matters beyond stellar collapse. The same comparison technique used to catch a vanishing star is also the exact method scientists plan to use to track objects that do not belong to our solar system at all, visitors passing through from other star systems entirely. Early analysis of the calibration frame's outer edge revealed a faint point of light following a trajectory unlike anything orbiting our sun should follow, moving too fast and on too strange a path to be a normal comet or asteroid. Researchers are still analyzing whether this point of light represents a genuine interstellar visitor, but if it does, it would mean the very first test image this observatory ever released may have quietly recorded a guest from another solar system before anyone even knew to look for one. Everything described so far, the hidden galactic stream, the impossibly fast asteroid, the vanishing star, the possible interstellar visitor, all of it belongs to the universe we can actually detect with light. But researchers say the true purpose behind building this observatory has almost nothing to do with what we can see directly. It has to do with what we cannot see at all. Roughly a century ago, an American astronomer named Vera Rubin studied the way galaxies spin. She noticed something that did not add up mathematically. Based on the amount of visible matter inside these galaxies, they should have been spinning too fast to hold together, flinging their outer stars off into space. Instead, they stayed intact, as if something invisible was providing extra gravity that no telescope of her time could detect. That invisible substance is what scientists now call dark matter, and Vera Rubin's careful measurements became some of the strongest early evidence that it actually exists. She passed away before ever seeing a telescope built and named in her honor, but researchers say this entire 10-year mission is essentially a continuation of the exact question she first raised decades earlier. What is actually holding the universe together? Scientists plan to answer that question using a method called photometric redshift, which sounds complicated but works on a fairly simple idea. As light from a distant galaxy travels across the expanding universe toward Earth, it stretches out and shifts toward the red end of the light spectrum. The more the light has stretched, the farther away that galaxy sits, and the older the light actually is by the time it reaches us. By carefully measuring this stretch across billions of galaxies, researchers can build a three-dimensional map of how matter, including invisible matter, is spread throughout the cosmos. Early results from this exact test image already show the redshift measurement technique performing at a level comparable to established leading telescopes, according to researchers reviewing the calibration data. Once the full 10-year survey is complete, scientists expect to measure the redshift of several billion individual galaxies, effectively building the most detailed map ever created of where the invisible skeleton of the universe actually sits. Dark matter is only half of that invisible puzzle. The other half is dark energy, a mysterious force that appears to be pushing the universe to expand faster and faster, rather than slowing down over time. Nobody currently knows what dark energy actually is, where it originates from, or whether its strength has changed throughout cosmic history. Researchers hope that by tracking hundreds of thousands of exploding stars called Type 1a supernovae every year, once the survey reaches full speed, they can finally test whether dark energy behaves as a fixed, unchanging force, or whether it has been slowly shifting since the early universe. If it turns out that dark energy is changing rather than constant, scientists say that finding alone could force a rewrite of some of the most fundamental assumptions currently held about how the universe will eventually end. Step back and look at everything one routine calibration photograph managed to contain. A faint stream of stars stretching further than the width of our own galaxy, sitting undiscovered until a sharper camera finally noticed it. A small asteroid spinning so quickly that it should, according to standard physics, be tearing itself apart, possibly a surviving fragment of a planet that no longer exists. A star that appears to have vanished without an explosion, potentially collapsing directly into a black hole in complete silence. A faint point of light on an unusual trajectory that may turn out to be a visitor from another solar system entirely. And underneath every single one of those discoveries, a redshift measurement technique already proving it can help map the invisible scaffolding of dark matter and dark energy holding the entire universe together. All of that came from one test image, taken purely to check that a camera worked correctly. This observatory has not even started its official 10-year survey at full strength yet, and it has already reshaped how several fields of astronomy are approaching their own open questions. So consider what that actually means going forward. If a single calibration frame produced this many unexpected results, researchers are left wondering what waits in the very first full year of real operation. How many more silent stellar collapses are sitting undiscovered in old, unexamined data? How many interstellar visitors have already crossed through our solar system without a single person noticing at the time? How many more fragments of long-destroyed planets are still spinning quietly through the asteroid belt, waiting for someone to finally point the right instrument in their direction? Astronomers spent generations assuming the night sky was fixed and unchanging, a backdrop that barely moved across an entire human lifetime. One accidental test photograph has already started proving that assumption wrong, and the real survey has barely begun.